Hello everybody, my name is Josep Manguez and jointly with Jose Núñez, my colleague from the IP Technologies area and other colleagues of the IP Technologies area of the CTTC, we are presenting you the demo that we prepared for the project BFEMTO, which is a European project that just finished. And in particular, this contribution is about a proof of concept, so it's a real testbed that we deployed here at CTTC on routing and load balancing in what we call a network of femtocells. We have other videos in our wiki where we explain what a network of femtocells is, but to briefly summarize the idea, the basic idea is to provide flexible mechanisms so that you, for example, in a stadium, in a large corporation, or even small ones, or in temporary deployments like conference halls, you can quickly and easily deploy femtocells. And we also, in the project, we also define entities both at the mobile network layer and at the transport network layer to confine the traffic as locally as possible inside the network of femtocells, so that you can access, for example, local services in the network of femtocells without going to the core necessarily. So we have defined all these entities, and what we are presenting here is mainly an improvement of the transport network layer, specifically designed for exploiting as much as possible the wireless resources, because in our case we have all wireless networks of femtocells, meaning that we form a mesh of networks of femtocells and they are wirelessly interconnected in the form of a multi-hub wireless network inside the company or the stadium or wherever we deploy that. So let's proceed with the demo, but before going to the demo, let us introduce a bit the main concepts of what we are showing in this demo. So, again, we also have other videos in our wiki explaining the main ideas, but to briefly summarize, this slide gives you the main ideas behind our scheme. So, in our routing scheme, we don't build routes, as in conventional routing protocols used in multi-hub wireless networks, but we take decisions on a per packet basis and only based on the local information exchanged between one node and its neighbors. So the basic idea when we take routing decisions is to gather information from the queueback logs of neighboring nodes, and this is the delta Q parameter that you see in the weight that we calculate for each link. And this delta Q is the Q differential between the queueback log of the local node taking the routing decision and that of each of the neighboring nodes. So we have such a delta to build a different weight for each of the links. So this is the, let's say, backpressure component of our routing scheme. And then we have a second component, which is the function PIJD, which basically provides the geographic component. So in this case, and you have the definition of how, in this case, in this specific proof of concept, we define this penalty function, P comes from penalty, which tends to, let's say, prioritize paths that towards neighbors that allow a certain packet to reach the destination through the shortest path. Then, when we combine both this backpressure component and the other geographic component in the form of this P function, we weight both parameters through this V parameter that we have next to function P. And this V parameter is very important, as you will see in the real-time demo that Jose will show you afterwards, because by appropriately weighting this parameter, and this is what is illustrated in the figures below, so what these figures below represent are It's a 10 by 10 wireless mesh network of femtocells, and this is for a low V parameter, which means that we mainly take decisions based on Q-back lock and the congestion of the nodes. So this basically means that we try to distribute as much as we can the resource consumption. This means wireless resource consumption, the Q backlog, or it could be any other parameter. But the main idea is that we distribute the resource consumption. As we increase the value of V, like in this case, or in a more extreme case, what we see is that we mainly take decisions based on getting as fast as possible, let's say, through the shortest path towards the intended destination. That's the basic idea. So our goal, as you will see, and this is what is explained in the lower part of the slide, our goal will be to adapt this V parameter depending on the network conditions, which mean traffic load or the congestion of the nodes or these kind of things. And we do that, as I explained before, on a per packet basis. So for taking and modifying this dynamically modifying this V parameter, we take into account not only the absolute value of the Q-back lock of the nodes, but also the rate at which the Q-back lock increases. And based on that, we modify the value of V for taking the decision for the next parameter, for the next period. And the other important thing is that we do it on a per packet basis in the sense that we also take into account other parameters of quality of service, if you want, of the packet. In this case, for this specific proof of concept, is the TTL that we are using. So if the TTL goes below a certain threshold, then we increase the value of V so that for this specific packet, but only for this specific packet, we go through the shortest path and as fast as possible to the destination. Otherwise, it will consume resources, and in the end, this packet will be discarded. In other implementations of our scheme, we could use any other DSCP value in the header or some other definition of flow that you may want. So this is the basic idea of our routing protocol. And what is the setup that we deployed for bFemto? So this is the plan of the first floor of the CTTC building in Barcelona. And the basic idea is that we deployed 12 nodes consisting of each of them of what we could call a wireless home node B, where we have a femtocell, a commercial femtocell, a 3G commercial femtocell in this case, because at the time we started the project, there were no LTE femtocells, so the proof of concept is with 3G flows, though the architectural reasoning in bFemto is more on EPS. But in this case, the basic ideas are the same, so it would be applied to an EPS system without problems. So the basic idea, as I said, is that we have 12 such nodes, and in this case, for the demo that you will see, we have deployed 3 UEs, 3 user equipment with its corresponding card, conventional ones, that will attach to 3 of these other nodes. So this is one UE that will attach to this femtocell. This is another UE that will attach to this other femtocell. In this case, these 2 femtocells are in the room that we are recording the video, and then we have another one in the first floor of the CTTC, but the scheme is still the same. So in our demos, in all the demos that you will see, the flows will be generated by these 3 nodes. And all the rest, so the traffic in the end will go this way. So the UE will generate a 3GPP flow, then through a regular UU interface, you will reach the wireless home node B, and then through 5 GHz Wi-Fi multi-hop, we will reach what we call the local femto gateway. The local femto gateway is an entity defined by bFemto that deals both with the mobile network layer, so as to try to confine the 3GPP procedures to the network of femtocells,
but also in our case it's our aggregation point of the traffic generated in the old wireless network of femtocells, because from the local femto gateway, then through the IUH interface, we reach the core emulator that we have in our lab, in what we call the extreme testbed, in the second floor of our building, and then to the external node, which is emulating the internet. And all these, and what we have in the lower part of the slide, as I said, all this is controlled by the extreme control network through which we synchronize machines, we execute the experiments to generate the flows, and so on. We have another video in the wiki describing how the extreme testbed works, if you're interested. So, in terms of testbed, let me give you a bit more detail of what is a wireless home node B. So, in this slide, what you have is a picture of one such wireless home node B, composed by a commercial femtocell, in this case a Sagemcom femtocell. And then what you see below the femtocell is a small form factor PC where the logic of our routing protocol works. So it's a Linux machine where we put this, the logic of our routing protocol. In the figure you also see that we could build multiple radios, though for this proof of concept we are just using one for the backhaul. And in terms of protocol stack, it's a regular IUH stack. So the leftmost part, this part over here, is the protocol stack of the conventional, the 3G femtocell, the commercial 3G femtocell, offering a UU interface towards the UE. And then this is our wireless mesh router, which is the one in charge of handling all the traffic coming from the femtocell in the multi-hop wireless network of femtocells. The important thing here is that we put our logic here. And how did we put that? The interesting thing is that we reused the code, exactly the same code that we developed for our simulations in NS3. And we did that through the NS3 emulation framework. Of course, for the specificities of our protocol, we need to take into account the Cubac log of the buffers of the real device. So there's some sort of communication. But the logic of the protocol, which is implemented in the NS3 IP stack part, is exactly the same as in our simulations. And this specific part of the routing scheme did not need any modification. So let's move now to the evaluation. So after this introduction, let's first start by generating a single flow to show you how, what are the implications of fixing V or putting a variable V. So in this case, in the first experiment, one of the UEs that we have in the room where we are recording this video will generate a flow, let's say, in the uplink direction towards the local femto gateway, and after that to the external node, which is in the top right part of the slide. But we are focusing here to show you how things evolved in the old wireless network of femtocells. So this flow will go straight to the local femto gateway, because in this specific experiment we have a fixed value of V. So we are not modifying depending on the conditions of the network. It's a fixed value of V and a high value of V, meaning that we are interested in reaching the destination through the shortest path. So based on our geographic information, we'll go straight to the destination. And this is what Jose will show you now real time.
This is the graphic user interface that we developed within the context of the bifemto project.